All right, for Physics 110 lab this week, we're going to be discussing multimeters. Multimeters are meters. These are devices that are used to tell us different values within an electrical circuit. So we'll discuss a few things that this can tell us and of course how to use it. But first I wanted to start with the idea of what exactly is an electrical circuit. So an electrical circuit is going to have different types of components in it to perform a function, or in this case I could have something very, very simple where I'm going to have what's known as a resistor. I have a couple different types of resistors here. This is a carbon-based resistor. I also have a power supply, okay? Something that's going to supply what we'll refer to as potential difference or voltage, and I'll define that in a moment for us. But this is going to supply our electricity, so to speak. And we have a component that we're going to run the electricity through to do something. In this case, all it's going to do is heat up. And so it can supply some heat if we'd like. The wires that I'm going to use here are conductors. They're going to allow the charges to flow freely and run through this device and do whatever it is that we'd like it to do, whether it be a light bulb, a resistor, a transistor, a lot of different options we could have there with those. So a circuit requires not that I just simply connect up one place, okay? So I could have one wire connecting this, but this will do nothing because I need a return path for the charges. So in other words, I need a way to get from a level of higher potential down to a level of lower potential. So one analogy that could be used for this would be thinking of taking a ball from the top of a mountain and allowing it to roll down, or allow water to flow down the mountain might even be a better analogy for that. The water itself would be the electricity flowing through the wires, and so we could look at the current of that, which would be analogous to the current flow, of course, of a river going down a mountain. And resistance could be what the terrain is like. If it's really smooth, then the water could flow pretty freely, but if it's very rocky and lots of twists and turns and rough soils, then that could slow the water down, of course. So in our case, that would be a higher resistor. So it would slow the flow of electrons through there, or the flow of electricity. And then, of course, the potential itself here for the water to flow, the greater potential difference or the greater voltage that we have here, then the more electricity I can flow through in a given amount of time. Well, the analogy to that would be a taller mountain, let's say, or a taller hill. So the higher that hill is. Now what I don't want you to do is to think that that potential difference or voltage here is going to be the same thing as, or is going to provide the force, like gravity provides a force to get the water down the hill. This is not providing the force. The force is going to be known as the electromagnetic force, or simply you may talk about this in class as being the Coulomb force. So the Coulomb force would be the force that would cause the charges to move. So you might have heard this very simply put before as like charges repel and unlike charges attract. In the case of gravity, anything with masses is going to attract. In the case of electricity, if you have two charges, then they'll either attract or repel depending on what their relative charges are to one another. The voltage or power supply that's here is going to allow us, the greater I have this, the greater my hill would be, so to speak, okay? So it's not a direct measure of potential energy like you would think of in measuring energy due to height difference when you do potential energy due to gravity. Not directly analogous to that. Think of it more as potential difference or voltage being the fact that the mountain is actually there. Okay, so because it's there, it's going to allow the force to, which in the case of the mountain would be gravity, to cause water or a ball, whatever you'd like to think about there, to go downhill. Whereas in this case, it's going to provide the force to allow charges to move from one potential to the other. Okay, so a completed circuit is relying upon having a complete path for this. So in other words, if I disconnect this at any point, or if I had a loose connection by disconnecting one of the resistors here, then there would be, so for example, if I did this, even though I leave the wires in place, this would then not allow, if I had current flowing in this direction through the yellow wire, it would get here with no place to go. So I still have a potential here for it to flow. But until I connect to this back in place, that's not going to happen. So it requires two things. One would have to be the voltage itself, and then a complete circuit in order for the circuit to operate. Okay? One of the things that you do run into, of course, is resistance. So let's define those very quickly, a little more formally. Looking at the variable, the first variable that I've been mentioning here is potential, or I keep referring to potential difference. I'm going to shorten that there. We use a capital V to represent potential. When you say potential difference, you put the delta in front. And when I talk about the units here is a capital V as well. Okay? So you've heard this referred to as volts or voltage, as you heard me refer to that before. So and scientists do this sometimes as well. We become a little lazy. People in general do this, and the general public would do this, is we'll use the term voltage to when we really mean potential difference, because we're talking about the variable. But we use the unit along with the, in place of the variable name. So an analogy to this would be, let's say we had the variable of distance and we referred to it as mileage. Mileage would be a specific unit. So just don't get too confused by that, because you will see a capital V in two different places, one being a variable, one being a unit, and that does get a little confusing. And just know that we make it even worse because we interchangeably use those words, and I'll be doing the same thing today. But once you understand that, I think that makes it a little easier and not quite as confusing. Current's a little straightforward. Current, we use a capital I. Still not quite as easy because we didn't use C for that. C gets used elsewhere. But for the units, we use a capital A. Okay, so again, I'm going to put brackets here so we can separate this. A is, you've heard this referred to as amps, or more formally, amperes. And then resistance, we use a capital R for the variable, but the unit is a Greek letter omega and is called ohms. Okay, so that gives you the variable and the unit for all three. There is a relationship that you will probably talk about at one point, which is called Ohm's law. And I'll write that down here just real quickly because you will come across it, but it's a very simple relationship that works for many different types of electrical components. Not everything is held to Ohm's law, but most components that you'll deal with certainly will. So Ohm's law being delta V equals IR, and this is a nice simple relationship that sees that, for example, if I were to increase the voltage, then I would have to, and let's say I kept my resistance the same, I would have to increase the current. Or let's say that if I kept my voltage the same, but I increase my resistance, then my current would have to go down. Okay? So we'll see some of that occur here. So mathematically it's there, but it also makes sense as we'll talk about it throughout the lab. Okay? So two other concepts here that we're going to talk about is going to be series and parallel. Okay, so if we take a look in the lab manual, we'll look at figure 1. And we'll see an example of series and also an example of a simple parallel circuit. Now, before we can really understand anything about these two circuits, we first need to discuss what the symbols mean. So the plus and minus that you see in circles here is referring to the potential difference or the voltage, as I said, using interchangeably earlier, but the power supply or the lab jacks that are on the stand. Then the next thing you notice is something that is what I'll say is a jagged line here, okay, the squiggle line or jagged line. This is a resistor, okay? And then they are using a straight line to be a wire, and if they have a straight line with an arrow in it, that's when they're referring to the current, okay? Which direction the current may be flowing. Okay, so now that we've got that out of the way, let's talk a little bit about what series and parallel mean. So when you wire something in series, it is possible to have both a series and parallel circuit in the same, wire things series and in parallel in the same circuit. But we're going to look at the very simple ones of just straight series circuits and parallel. So the best question to actually ask is not is it directly a series or a parallel circuit, but more so are two components in series or parallel with one another. So for example, let's say I have this in the series circuit. Let's say I'm looking at both this resistor and this resistor, and I want to know, are they in series or parallel? Well, the way you can tell that is by looking at the number of direct paths between them. What I mean by that is if I were to follow the path to go from, let's say, this point to this point, I see that there is one direct path here. But if I try to go from, let's say, this side to this side in either direction, I would have to go through this voltage source here, through the power supply. So in other words, not a direct path. So all I have is one direct path there, and that would classify it as a series set. So if I look at these other two resistors here, so I have a resistor here and a resistor here, are they in series or are they in parallel? Well, in this case, if I try to go from this side to this side, there is one direct path. If I go from here to here, or in the other direction, either way is fine, I see that there is a second direct path. In neither case did I have to go through anything else. There was no other resistor, power supply, or other electrical component. So in this case, I have two paths between those two components, and therefore they're in parallel. When we talk about the meters themselves, there are a few components to point out. There are four, on this particular meter for these flukes, there are four places that I could plug wires into, okay? All of these are known as banana jacks, banana plugs. And so these just simply plug in like so. And if you look here, you'll notice that there's one that says COM, and it's got the black. Sometimes people refer to this as the negative, ground. In this case, COM stands for common. So the way I like to think about that is common to all of these here, which means that you will always plug something in here, okay? So the only other choice is, which of these three do I use to make a measurement? Well, if I want to measure voltage, then I'm going to use the capital V to measure volts, right? If I want to measure potential difference, that's what I'm going to use. If I was going to measure resistance, you'll notice there's an ohm, an omega there, which stands for ohms, for resistance. If you wanted to measure current, you'll recall the unit that we use is amps, or a capital A. And you'll notice this says 10 capital A. This says 300 little m capital A. So 10A, 10 amps, this means 300 milliamps, okay? So you could use, if this says don't put more than 10 amps of current through this, because it could damage the meter if you run more than 10 amps. And this says don't run more than 300 milliamps through this here, okay? So this would be a more sensitive side. This will give you more decimal places if you plug it into the 300 milliamps. But you can only run a very small amount of current through that, relatively speaking. So if you have a larger current, you would have to use this one. If you have a smaller current, you would have the choice between these depending on how many decimal places you would like to read that to. Okay, so again, always something in the common. If you're measuring the potential difference or volts, you would need to use this input. If you're using current, you choose between these two. For our low current usage, we're typically going to use this, but I'll always start with that to make sure that it's going to be there. Okay? Okay, so we're going to start with the exercises. And the exercises are going to be a few different circuits that we're going to build, and we're going to make different measurements there. If you look at step 1, we will notice that they show bench jacks, the voltmeter, they're showing you a pictorial representation, whereas the one over there with the lines and the big V and so on to the left in figure 3, that is a schematic representation. Okay, so this is exactly what I did at the very beginning of the lab, and that was to take a voltmeter. Now that we understand a little bit about the multimeters, and if I want to measure voltage, I know that I'm always going to have something plugged in the common, okay? And then I'm going to plug in something into the V because I want to measure voltage, because that's what they're asking us to measure here, is the potential difference. Then we are going to select with this dial what we would like to both turn on the meter, as well as what type of measurement we need to make. So in this case, if you look at the voltage, you'll notice the capital V, so obviously that's what we're going to use. We're going to choose between these two. One of them has what looks like a sine wave above it. That's referring to the alternating current, meaning that it was moving back and forth. That's not what we're using for this lab. We're only doing DC. So therefore, we're going to use the one that has the straight and the dashed line over top of the voltage, over top of the capital V there. So when I switch to that, I'll see that I'm reading nothing at the moment. And that's because, I'll leave this up here so we can see that. I'm going to plug in to the ground into the green plate, and then the red plug is going to get the yellow. And from that, we'll be able to, again, of course, see 5.07 like we saw at the very beginning of our discussion. Okay? So, at that point, I'm just going to record this down and write it for you, and I'll share these notes with you later. All right, so the next thing to do is to look at the second circuit that they'd like us to set up. There is something I would kind of like to point out about these two circuits that you see next, both B and C. If you take a look at both of these circuits, you'll notice that if you ignore the voltmeter, if you take that out, then next what you'll see is that if I follow around here with the red, you'll see that I have exactly the same circuit. The only difference between B and C is where we're going to place the voltmeter, okay? So when we get ready to wire this, I'm going to use that idea to make this a little simpler for us to be able to wire. Is I'm going to go ahead and wire up just the main circuit first, and then we'll add the voltmeter on second. And that's a strategy that I would encourage you to use for any other circuits that you wire. Okay, so before we can go on to talking about the circuit, the first thing that we also need to understand about the schematic that we have here is there's one more complicating factor, and that is if I were to look at this device right here, okay? This is what's known as a rheostat or a variable resistor. To look at this, I'll see that I have this squiggle line here, or the jagged line, and I also have an arrow that is pointed at that object there. Okay, so let's now take a look at the physical representation of this. Okay, so looking at the jagged line, that is meant to represent a coil of wire. And so what we see here is a wire that starts at this point and wraps its way around this tube. Okay, so coil of wire wraps its way around the tube, and there are two ends. So the wire itself literally comes out here and starts over at this point here. So these two ends of the wire are what I have marked on the, there's one end, and then you'll there is a bar that goes across the top, and there is this little slider that's on top of this. If we can get this, you might be able to notice that there is a contact point here. It's a little hard to see, but you might be able to see that on the camera. And as I slide this along, this is allowing that point to touch this coil of wire any place it would like. Okay? So the distance of this bar is extremely low, okay? Basically nothing compared to the rest of what we have. So the idea with this resistor is that the coil of wire, if I went from one end to the other, I would be going through the entire length of wire. So there are a couple things that can affect resistance. One, of course, as you might imagine, is the type of material. Certain materials are going to have higher resistance to electrical than others. Some don't let electricity flow at all. We call those insulators. But for conductors, the different types of materials, some are better at transferring electricity than others. So the type of material matters. Turns out things like temperature, the size of the wire, but also the length. The length of the wire matters. Okay, so the longer the wire, the longer the resistance. The way to think about that is that if this piece of wire is giving any resistance at all, the more you have to go through, then the more energy you would be losing to make it all the way through if you have to go further. Okay, so it's a pretty easy idea to understand. So in this case, it's called a variable resistor because if I flowed all the way through, I would get the full resistance of this piece of wire. But because I have this bar on top, I can move it along here and select where I would like the current to leave. So because it's in contact, if the current was coming, let's say if I plugged it in here, then it would start to wrap around. It would get to this point very quickly, and then it could leave out through this very low resistance top. But if I move it over in this direction, I have much more wire to go through. So my resistance would be higher. So if I were connecting up this point and this point, this would be low resistance, this would be high resistance. Okay? So we'll use that idea to make notes of our observations as we move along. Now that we understand that, let's talk about how to wire up this circuit. So the way I like to do this is to point to start. Okay, so let's say I start here at the negative, and then I'm going to follow along and go the shortest possible path to return back to where I started. So moving along this until I get to this point here, that is going to be a jagged wire. And of course that is referring to a resistor. But in this case it has an arrow pointing to it, which means the variable resistor that I was describing just a moment ago. So I know that I'm going to connect up the resistor. So where I've drawn this blue line so far, let's look at that physically. Let's start from the ground, okay, which would be this point here. And let's take it all the way until we get to a variable resistor. All right, you'll notice when I drew the blue line here, I started at the ground and I moved my way till I got to the variable resistor, which is here. Okay, so there are two ends to this wire. So when you look at the picture, two ends to the wire. There's an end here and an end here. Okay, so I'm going to plug it into one of those ends, and then I'm going to come from the arrow part that's represented here and follow it around until I reach a fixed resistor. So that means I'm going to leave out of this point here. So that was from the arrow itself. This would be the arrow representing where I pick along this wire. And I'm going to take that and move along until I come to a fixed resistor. Okay? And the fixed resistor here they're referring to as the 100 resistor. In this bank of resistors, the top one is 100 ohms and this one is 180 ohms. So I'm going to come to this resistor. Okay, coming back to the schematic, I have plugged in my wire to this point, and then I'm going to pick up from the other side of the resistor and follow back to the positive. Okay, so that means coming from, I'm going to, maybe I'll pick a different color there to make this a little more obvious. The color of the wire does not matter, by the way, because they're all copper wires. So if you take the color off of them, they're all exactly the same. It does make it easier to visually identify what's happening in the circuit. So I'm going to go through the resistor, come out, and take my way back to this point here. Okay? So again, the circuit we followed from the ground, and we moved from the ground all the way over to the fixed point here. We go through this coil of wire and leave out through the arrow or the wiper, sometimes it's referred to as a wiper, but the variable point of the resistor, and move out through here over to through a fixed resistor and then back to here. Okay, so again, right now if I take these wires out of the way and make this a little easier to see, at this point I have a complete circuit. Okay, I've got a connection point here, here, I go through this guy, come out, go through this one, and come out the other side. So that's a complete circuit. Now the meter's job is to make a measurement to help us understand what's going on in the circuit. Okay, so if we look back at B, we know, or the we notice that we have the voltmeter here, and the voltmeter is going to be connected up to the circuit. And one place that people get confused is when they try to connect this in. So let's look at this drawing. If we leave from the voltmeter and go in this direction, then I get to this point and people say, well, now what do I do? Do I go here or do I go here? Okay. Well, in this case, it would not make any difference which end of this I plug in. I think it's visually better to go directly to this guy here, as you'll see in a moment. Same thing would occur on this side. I would come over and connect up on this point. Okay, so these are the 2 points that I want to connect to, both the arrow and the fixed point of the rheostat, of the variable resistor. Okay, so let's take the meter and let's pick a couple of wires to work with. Okay, and keep in mind again we have the common. So the common is where I'm going to start with on the voltmeter. Okay, so I'm going to plug something into the common, and looking at my drawing, I see that I would want to take one of these back to the fixed point of the resistor, so that would be here. Okay, these will stack on top of each other, and then I want to take the volt connection, okay, the voltage connection. So I want to read the volts, the potential difference here. I'm going to take that and connect it over to the variable part of the resistor. Okay. So you can see that this voltmeter is across this particular resistor. All right, now taking a look at this, they'd like us to record some of the values. So I'm going to start down at a low resistance. Now this is all just observational. Okay, it's a little different for the labs. You're typically recording a lot of values and comparing those to known values or other values that you've determined through different ways in the experiment, either theoretically or experimentally. And in this case, it's going to be a little different because we're just going to be making observations to see what's happening inside the circuit as we make changes. And so what I'm going to do here is I'm going to make a couple of notes and say that at low R, low resistance, okay, we're not measuring it directly, we just know this is going to be a low resistance. And how do I know? Again, it's because if I'm connected here, I have a very short bit of wire to run through before I reach where this arm is. Whereas if I'm over here, I have a lot more wire to run through to get out this point here. Okay, so a small amount of wire here means a low resistance. And at a low resistance, I'm just going to read off what my voltage is. I see the voltage is 0.134. Okay, so at low R, then my potential difference is 0.134 volts. All right. So next, to record down the high resistance, okay, and record down what my potential difference will be there. So let's take this over to a high resistance, and we'll see that our value now is about 1.395. So I'll record 1.395 volts. Okay, so great for that. Now, next thing we're going to do is we are going to go down and take a look at the next circuit. Now again, recall that I said that B and C were the same circuit. The only difference is where we place the voltmeter. Okay, so I'm going to take the voltmeter and remove it from this place, okay, and connect it up as we see in the circuit. So at circuit C, I see that, or figure 5 here for the schematic for circuit C, I notice here that I can connect up my voltmeter across this 100 ohm resistor here. Okay, so the 100 ohm resistor is the guy that's here on this board. Okay, the top one here is the 100 ohm resistor. So I'm just simply going to connect up the 2 wires across that. And let's do the exact same measurement this time. Let's take a look at the high resistance. And I see that at the high resistance, my value is 3.66 volts. All right, so I'm going to write here high R. My voltage or my potential difference is 3.66. Okay. Now at low resistance, which means I add this back over to this point here, see that I get 4.95. Okay. This is not going to line up exactly, but remember before that we had about 5 volts. Okay, I'm going to round these numbers just a little bit. We had about 5 volts to start with. Okay, I have not changed my voltage that's being supplied to the circuit at all. The only thing I'm actually doing is changing the resistance here. So earlier we saw that if I take the voltmeter and measure the voltage across the variable resistor, and I think what I'm going to do, I'm going to go ahead and wire this up so that we can have these two side by side, make this very obvious. Okay, so now looking at this guy here, this is going to read the voltage across for this resistor, for the fixed resistor. This is going to read the voltage here. So we'll notice at low resistance, we have a smaller value. This one has a higher value. When I go here, I'm going to see that this has dropped, has increased. All I did was increase my resistance. So what's going on? Well, this voltmeter measuring across here is that when I have a low resistance, then I see that I do not need much voltage here, which you can think of it as I need less voltage to push current through because, or to allow the current to flow through here because I don't have much resistance to that flow of current. Okay? As I increase the resistance, I need more of the voltage that's available to me there. So if you look at the values here, I see that I get about 1.4. Okay? I'm just going to round these values. Over here, I see 3.6. Add 1.4 and 3.6, you're going to get 5. Okay, that's how much total we have. So if I pick any point along through here, let's say the middle, I'll see that this value is about 0.9 and this is about 4.1. Okay, 4.1. Then I would add that up and I would get 5.05, which is very, very close to what we had earlier. Okay, I could drop this all the way down to a low resistance, and I see that this is 0.13. And I've got 0.13, yeah, that's correct. So that would give me about 5.05 again. We're still getting just that fraction more than 5 volts as we saw at the very beginning when we measured the voltage directly in the very first step, okay? So in other words, when you have a series circuit, the voltage across each of the different components that are wired together in series will be shared. In other words, you can add the voltage across each of those, okay, to add up to the total potential differences across the entire circuit or that set of the circuit, okay? So let's move on to D, and they're going to ask you to now use the one of the multimeters. So I'm going to just disconnect this multimeter completely, get it out of the way. And they're going to ask us to take one of the multimeters and connect it in series. Okay? So the way to connect it in series so that we can measure the current. So another way to think about this is when I want to measure the current in something, then I need to be able to allow that current to flow through. Think of, for example, water. If I want to know how fast the water, how much water and how fast it's moving, I'm going to have to actually put something in the water to sample that and get an idea of how fast that water is moving and how much of it has moved past. Same thing with electrical current. I'm going to have to place something there to be able to sample that and measure it. Whereas for the voltmeter, think back for a moment to the voltmeter wants to measure the voltage or the potential difference. In other words, it wants to know what's the potential at, and you notice when I did this, I would measure it something like this. We would be measuring the potential at this point, the potential at this point, and seeing what the difference in those are, okay? And I would not want any current coming through this. In other words, if the current was starting here and moving through this red wire, when it gets to this point, it could go through the green wire or it could go through here. I want it all flowing through this because the meter's job is to make a measurement, not to affect the circuit. So if I place the meter here, I don't want any current flowing this way because the voltmeter's job is not to measure current, its job is to measure the potential difference. So I don't want any current flowing through this. So the resistance for this guy is infinitely large. In other words, they're not even attached here. You want the resistance to be very high so that no current tries to flow through the voltmeter, okay? Whereas for an ammeter, and you'll notice, of course, that this is in parallel, by the way, so that you always have to have the voltmeter in parallel for that reason. We'll kind of see that as we move along. An ammeter, I want to be able to measure the current that flows through a circuit, and it will need to be in series in order for that to happen, okay? So if I were to look at a, in D, if you look at 6, I see that they've got an ammeter that is between the positive side of the power supply and the fixed end of the variable resistor. And we know it's a variable resistor because it has the arrow pointing at it, okay? So that means that in order to wire this up, I would like to place an ammeter somewhere between the positive and I'm going to go ahead and disconnect some of this here so that we can wire this just as they have it in the lab manual. All right, so at first, I would like to go from the positive to the ammeter, okay? So that's the left side of figure 6. And I'm going to start with the 10 amp jack. We'll talk about that here in just a moment, but we're going to plug into the positive side here. Then I'm going to come out of the ammeter, and again I'm using the common here, so I'm using one of the capital A's because I want to measure current, and I'm using common because we always use that, common to all the terminals. So I'm going to run from this over to the fixed point, which again the fixed point of the variable resistor is here. Then I'm going to come out of the arrow, which is the variable part here, and I'm going to take that and go all the way back to a 100 ohm resistor again, okay, so we're going to connect that here. And then we're going to go through the 100 ohm resistor and go back to ground, which is here, okay? So again, I've started at the, in this case I started through the positive. I went over and connected to my ammeter first. That would be this red wire here. Then I've left out of that with the green wire would go there. Then I'm coming out with this yellow wire, which follows along this point going over to the 100. And then finally, this blue wire would be this section that goes through here. Okay? So that's how we've gone about wiring those. Now, at this point, I also need to make one more adjustment to my multimeter. Right now, it's still set on voltage, okay, or measuring the potential difference or volts. I'm going to switch it over to the DC setting for amperes, or in other words, I want to measure the current, the amps, okay? You'll notice my value here is 0.05, which is less than 0.3. This scale is in amps. So if it's less than 0.3, that means it's below 300 milliamps, which means I can then switch down to this section here. I can pull this out and place it down here. As long as that's below 300 milliamps, it most certainly is, and you see I get more decimal places. So in fact, it's reading 43.2 milliamps. And so again, when I switch to this bottom down here, it does change the scale to milliamps automatically. So that's 43.2 milliamps, okay, for a low resistance. So let me make the measurements here. I'm just going to write this over. Low resistance, I see that I have 43.2 milliamps for this left-hand side. Now, taking a look at the difference between the left-hand circuit and the right-hand circuit that they have in figure 6. The one on the right, you'll notice, is exactly the same as the one on the left with the exception of one detail, and that is where the ammeter is setting, okay? So in that case, they have the ammeter between the variable point here and the 100. So in other words, they have ammeter somewhere between this point and this point. Okay, well the easy way to do that would be for me to simply disconnect this ammeter here. Notice I'm not changing my variable resistor yet. And then I can insert this between the variable part of this resistor and the fixed, and I see that my value now is 42.8 milliamps. Exactly, not quite exactly what I had before, but very, very similar to what I had earlier. So I see that it's 42.9 milliamps for a low R here. And then if I change this to a higher resistance, I would expect the current to go down because I'm increasing the resistance overall in the circuit. I would expect there to be a lower current, unless, in other words, a lower flow of electricity, so to speak. And I see that as I increase this over to a higher resistance, I get a smaller value of about 32.6 milliamps. So I'll have high R here, and that's 32.6 milliamps. And I expect to get the same thing when I back over. And about 32.6 again here. Okay? So so what we see is that the same value, the same reading for the meter, no matter where I place the ammeter in the series circuit, which makes sense because there is no other place for the current to go. Okay? No matter whether I place this here or here or here, it's always following along this same path. All right? So I expect no matter where I place the meter to get the same reading. Now, of course, the reading does change as I change the variable resistor, but overall, in terms of where I place the ammeter in a series circuit, it does not matter. So to recap those two, the circuit, reading the voltage across multiple things gave me a different value. And they would add together to give me the total potential difference for the entire circuit. Whereas for current, I get the same reading no matter where I place the meter. Okay? So let's now move on, and let's go look at E. And E is going to use two meters in conjunction. Okay? And so they've got a slightly different circuit that they've wired up here. So I'm going to go ahead and disconnect the wires one more time. Okay. And let's start this time over at the ground. So let's go from the ground. I've been using this wire quite a bit for ground. So in this case, I have the blue wire, and I'm going to go from the ground over to the ammeter. I'm going to connect those two up. Okay. So that's this wire, this connection here. Then I'm going to go from the positive side of the ammeter. And remember, I have a choice in this location, but I'm going to follow the innermost loop. And so going to get back to where I start. So we're going to move from the ammeter now over to the arrow, which is the variable part of the resistor. Then we're going to go from the fixed point of the variable resistor over to the 100 ohm resistor. All right, that would be that wire. And then finally, from that back to the positive. Okay? So let's take this wire and bring him all the way back to the positive there. Okay? So at this point, I still have a series circuit with the same things. Notice I didn't change my variable resistor earlier, so I'm still getting 32.7, so about almost exactly the same as what we were reading a moment ago. Probably just a different set of wires, so slightly different resistance in the wires, but overall I get about exactly the same reading because overall, even though my order changed, the same components are here and they're in series, so the current stays the same. Okay, so the last thing they want me to do is to connect the voltmeter up. So I'm going to take one side of the voltmeter and connect it over to the fixed point of the variable resistor, and the other side I'm going to connect up to the variable side. So I think so at this point, they're saying measure both voltage and current in a circuit. Okay, so I'm just going to make 3 different measurements here, and just so that we have some measurements, we can see how they relate to one another. What we expect to see is, again, we're using the voltmeter to measure the resistance, measure the voltage, sorry, across this variable resistor. So what we've already seen is that for low resistance, we expect the value for the voltage, for the volts across this guy to be low. And as I increase it, I'll expect that value to go up. Now, but as I increase the resistance here, I will expect my total circuit current to go down. Okay? So let's take a look at that value. Let's start at low resistance. Okay, so for a low resistance, I see that I'm reading 0.085 on the voltage. And I am reading 43.3 milliamps. Okay, let's go to a mid R, somewhere in the middle. And to see that our voltage has increased to 0.856. And the current has gone down 6.6 milliamps, as we expected. And then finally, I'm going to write, hi, sorry for the terrible handwriting. So let's move over to a high resistance, and we're going to see we've got 1.341 volts, and we see we've got 32.4 milliamps. Okay, so let's move on to the final parts of this lab to wrap things up. And we're going to be looking at parallel combinations of resistors. You're going to notice when you go look at F and you look at G, you will see that there are no arrows on any of those resistors, which means we are now finished with the variable resistor. Okay, so I'm going to go ahead and disconnect the meters and the resistors. And to make things a little simpler, I'm going to remove this guy out of the way, and we're going to stage the variable resistors, the fixed resistors here. So again, the top one is 100 ohms, the bottom one is 180 ohms. So I'm going to treat those the same way in the lab manual here. So I'm going to go ahead and, for F, I'm going to write 100 ohms, 180 ohms. That way we can remember what they are. So in this case, what they would like us to do is to measure the current. And you'll notice that they have in the first schematic the current down on the bottom left, then they go up to sort of what we'll call the middle branch, and then they go to the top branch with the 100 ohm resistor and place the ammeter there. Okay? So this could be a little tricky to wire. The one thing that, so I think what I'll do is I'm going to start with the very first one. Okay? So let's go from ground to make this really simple. Let's start on the ground side. And let's work our way over to the resistor. So we'll notice if we look at the ground side, then if I go from the ground on the power supply, and the first way to get the inside loop, so to speak, go ahead and mark this up here as we were doing earlier. I'm going to connect this part up by doing That's the 180 ohm resistor. I'm going to connect like this. Then let's come out of the 180 ohm resistor, and we can go back to the ammeter. So here's my ammeter. I'm going to come out of the 180 ohm resistor and go back to the ammeter. Okay. Then we're going to leave out of the ammeter and go back to the positive. So let's take this guy here and run straight back to positive. Okay. Now, let's go back to this and let's do this in green. Let's now go from the 180 ohm resistor and connect it to the 100. Okay, so I'm just going to take one of these wires here. And let's connect the 180 ohm resistor to the 100 ohm resistor. Okay. Then let's take the 100 and connect it. We can either go all the way back to the ammeter, or we can connect it directly to the 180 ohm resistor like this. Okay. So let's do that right here. Okay. So there, we've connected the 100 ohm resistor to the 180 ohm resistor. Now for this measurement, I'm now going to look at my at the ammeter in this case, and I read 68 milliamps. Okay. Okay, so let's go to the next part. Let's go ahead and draw in our, let's start at the negative. We'll go over to the 180 ohm resistor. So we'll go from the ground to the 180 ohm. That would be this wire here. Then we'll also take the, go from the other side of the 180 out to the ammeter. So that means we're going to go from this point, coming out of the ammeter, out of the 180. Let me get these out of the way so we can see what we're doing. All right, so we've gone from the ground, 180 ohm resistor. We're going to come out of this 180 ohm and go to the ammeter. Okay, so we have that. Then we're going to come out of the ammeter and take our trek back to the positive, and so that is this point here. Okay, and at this point, the only other thing to do is to connect up the 100 ohm resistor. And so let's look on this side over here. We'll notice that we can connect it directly back to the ground side here is fine. That means to the same side as on the ground. By the way, you'll notice that when I'm connecting this wire here, I'm looking at this side of the wire. And that means I would connect here. If I connect it the other way, it would change my readings there. Okay? So for the other side, I could go over and plug this into the positive side of the ammeter, or I could go all the way back to the plus on. So I could connect here, and I could go to the positive side of the ammeter. And you'll notice that my value here of 26.4. So at this point, I'm going to go ahead and record that value, 26.5. So you'll notice when you look at the third in F, you'll see that the ammeter is now going, is measuring the current going through the top one, which is the 100 ohm resistor. Okay, so in other words, one quick and easy way to do this is to simply swap the wires over to this point, so that then I could measure just the current going through here. So that's a little shortcut I'm going to share with you. That's 43.9 milliamps. Okay. And so what I hope you see here is that it's not something you have to point out. They're not trying to make this obvious to you. But since we've got a chance to do the explanation as we go along, you may notice that if you add 44 and 26, you would get something pretty close to 68 there. There's a slight bit of difference in there, and there's a couple reasons for that in terms of resistance that we're not taking into account. The final section is for the voltmeter for a parallel set. Okay, so to do that, I'm going to go ahead and take this ammeter out. Now, for clarity for this one, I'm going to take a slightly different approach, okay? I'm going to, I could follow along like we did earlier, or I'm just simply going to show you that if you take a look and you look, let's see if I can draw this out here. You'll notice that the voltmeter, remember I said before, I could take it here, I could take it here, or I could take it all the way back here, okay? Let's look at this voltmeter. I could go here, I could go here, or I could go here, okay? Same thing would apply here, 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 or I could connect it here. In other words, what's the difference between all three of those circuits? Absolutely nothing. Okay, they're all the same even though they visually look different, okay? So let's verify that idea by wiring these up in these parallel set. But what I'm going to do is I'm going to wire this up once without the voltmeter first, and then we're going to add the voltmeter back in and see how that works, okay? All right, so to do that, I'm going to connect a ground. We'll just follow along and do the ground to one of these resistors. Then we're going to take a ground and go to other side of one of the resistors. Then we're going to go ahead and plug up a positive side. So I think I'll do all these the same color. Like so. Okay, so now I have a parallel set of resistors. Now let's take my voltmeter and maybe looking at the first, let's say that visually to me that almost looks like the voltmeter is going to be measuring, if we were to write these two out, maybe I'll do this real quick over here and say that this is the 100 ohm resistor is the top one, and the 180 ohm resistor is the bottom one, just for visual reference. It won't make any difference, as you'll see in a moment. So if I let the voltmeter be that, it looks to me like from a top-down view that the voltmeter is measuring the voltage across the 180 ohm resistor. Okay, so let's do that. Let's see what we get here. Actually, I'll wire these the opposite direction, which this brings up a good point I'll show in just a moment. But so when I do that here, I notice that I get 5.04, very similar to what I got earlier. You'll notice that when I connect these wires in the opposite direction, okay, so that now I have the common connected over to the side that's on the same side as the positive here, then I have the polarity of this reversed. So that's not a problem at all, because as you've been learning in physics occasionally, is that the magnitude of the value matters, and that we use the positive and negative to represent a direction. So in this case, I see 5.04 and I'll see a negative sign. But if I were to reverse these two, I'd get the exact same value, this time just as a positive. Okay? So that's just a little note I wanted to make about the positive here. So I see right now I've got 5.04. So the if I go to the next one, the middle drawing there, the middle schematic, it looks to me like the voltmeter's reading across the 100 ohm resistor, just visually. So I could take it over here and put it across the 100 ohm resistor, and I see that I still get 5.04. Then for the third, it looks like perhaps it might be measuring this guy back here. And as we already know from earlier, if I plug that in, I should get 5.04 again. Okay? So I'm going to go ahead and write those values down here for you. And again, you'll just write up your observations about what you've seen today in the lab, and hopefully be able to use my explanations, hopefully understand it. Certainly don't repeat it word for word what I've said, but hopefully understand that and be able to write in your own words what you've seen and a little bit about why. Okay, and I've added a couple of extra notes in there that weren't necessarily things they were specifically talking or asking about in the lab, but it's to help tie that in with anything else you might talk about in lecture at some point. Okay, so be sure to ask your TA if you've got any questions, and good luck and have a great week.